Machine and regular expression and their application to electrical analysis part 3. So this is the third part and this is the last part. Here we will conclude this topic. So let us start with the conversion of NFA to DFA. So the algorithm will take NFA as a input, NFA N as a input, DFA D as a accepting, DFA D output will be DFA D, which will accept the same language that is accepted by the NFA N. The method. The algorithm constructs a transition table DTran for DFA D. Each state of DFA is a set of NFA states, and we construct DTran for DFA D. So D will simulate in parallel all possible moves NFA N can make on a given input string. First, we will deal with the epsilon transition of NFAN properly. We define epsilon closure of a state and move t comma a function on a state of NFAN that are needed in the algorithm. We consider small s is the start state of NFAN, and while capital T is a set of states of NFAN. So epsilon closure of start state S. Set of NFA states reachable from NFA state S on epsilon transition alone. What is epsilon closure of capital T? A set of NFA states reachable from NFA states S in set T on epsilon transition alone. Next we have function move T comma A. This is the set of NFA states to which there is a transition on input A from some state S in T. Explore those set of states that N can be in after seeing some input string. Before reading the first input symbol, NFAN can be in any of the state of epsilon closure of S0 is its start state. For the induction, suppose NFAN can be in set of states T after reading the input string X. If it next read input A, then NFAN can immediately go to any of states in move T comma A. After reading A, it may also make several epsilon transition. Thus NFAN could be in any state of epsilon closure move T comma A after reading input XA. Following these ideas, the construction of the set of DFA D states and transition function DTran is shown following. So according to this algorithm, initial epsilon closure S0 is the only state in D states and it is unmarked, and while there is unmarked state T in D state, mark T for each input symbol A. U will be the epsilon closure move T comma A. If U is not in D state and U as a marked state of D state, D tran TA is equal to U. So this is the figure of the subset construction. The start state of D is epsilon closure of S0 and accepting state of D are all those states of N states that include at least one accepting state of N. To complete the description of the subset construction, we need only to show how epsilon closure T is computed to any set of NFA states T. This process is straightforward. Search in a graph from the set of states. Here we imagine that only epsilon labeled edges are available in the graph. So what we will do, we will push all the states of T onto the stack, initialize epsilon closure of T while stack is not empty, pop T to the top of the element of the stack. For each state U will with an edge of from T to U labeled on epsilon. If U is not in the epsilon closure of T, add U is to the epsilon closure of T, push U on a stack. So in this way, so this is repeated while stack is not empty. So this is the algorithm for computing the epsilon closure of T. Consider, let us take one example. Consider we have an FA accepting accepting a string which ends with ABB. Such an FA will be created when we construct directly from the regular expression. We will apply the algorithm start capital A. So start state of A, start state capital A of the equivalent DFA is the epsilon closure of 0. So 0 state. Now we need to find the epsilon closure of 0 state. So let us see if 0 state is connected with which states through the epsilon part. So it is connected with state 1, state 7, state 2, state 4. So epsilon closure will be 0, 1, 2, 4, and 7. So it can be represented by capital A. Now what we need to do, now we need to the input alphabet is A comma B. Now from capital A state we need to find A and B. So if there is input A from the state capital A, where we need to go? So this will be the epsilon closure of move A comma A. So second we need to find if there is input B, where we need to go. So each and every time we need to find the epsilon closure of the move A comma A and F comma B. Here A represents, capital A represents 0, 1, 2, 4, and 7. Now we will discuss in the next slide how we can move from capital A to another state if there is the input A and B separately. So here in the diagram you can see that if you are at state so we need to find here move A comma small a first. So since A is 0, 1, 2, 4, and 7, so from 0, 1, 2, 4, and 7 each and every time we need to find if we take input A, so where we will go. So in the diagram you can see move A comma A, there is 3 and 8. We can reach from this state to the state 3 and state 8. Now we need to find the epsilon closure of 3 and 8. So if you find the epsilon closure of 3 and 8, you will get 1, 2, 3, 4, 6, 7, and 8. This is the new state, so we can represent this set of a state by capital B. So it is represented by capital B. So it is represented by capital B. So now in the next slide, you will see if the input is capital small b. So we are in a state capital A, and if the input is small b, where we need to go. So we need to compute d tran A comma B. If you need if you find A comma B, so if we are at a state capital A and the input is small alphabet B, where we need to go. So the set of state is 0, 1, 2, 4, and 7. For each and every state we need to find B, and we need to find the epsilon closure. So here you can see that if A comma D tran A comma B, if we find it is only the state 5, only the state 5. So now we need to find the epsilon closure of 5. If the epsilon closure of 5 is 1, 2, 4, 5, 6, 7, 6, and 7. So now this state can be represented by C. So in this way we can proceed for each and every time. So if we conclude, we have a table, and first we have the set of the NFA state. The initial state is the epsilon closure of initial state. So this is the initial state of the DFA. Also this is the start state. Here you can see capital this set of state is represented by capital A. The new state was B. B was represented by this set of states, and C and A, if you can do it at the end by yourself. So finally the final state is 10, and 10 is present at the last state, that is the E state. So E state will be the final state. So we can draw it like this. A is the start state. B, if the input is small a, we are going to A. If the input is B, we are going to B. From the B, transition can be drawn. It's very easy to see the table, and we can draw the DFA accordingly. So from E, and finally from E. So this is the final DFA for the NFA. So in this way we can convert from NFA to DFA. Thank you so much. We will discuss the rest of the part in the next lecture.